So last spring I spent quite a bit of time on writing a program that generated that basically work as the basis of a maze. And so your goal for this program is to write a is to basically draw a path. Write a program that draws a path from here to here using depth first search. So in other words, going down these corridors and checking. You want to use the stack to accomplish this. Now, I'll get into the details of how we solve that in a bit, but let's go over this algorithm first. First off, or this program that I wrote for you first. Made up into 3 files. Now, as you can see, it involves a GUI, but nice thing about these GUIs is that you really don't need to know how this works. So the maze class is the class that you use to run the program. It's the main class. So it's got public stack void main, and it has new maze. That's what it creates. Now, a maze is a J-frame, which is basically a window. And these so let me go ahead and pull up this window again. So a J-frame is this thing. It is this title bar over here, and then it's not the contents in the window, but the stuff around it, like this border that I can extend and stuff. And what we put in it is a maze panel, right, which is the main bulk of the code. We say that basically on default, if I close it, I should quit the program, which is generally a good idea. We pack it up for the user. We set visible to true. This one sets it so that the screen size is 800 by 800 so we can see it. And these 2 parameters over here feed into the maze grid panel and basically say what kind of size maze did I want to generate. And it can get pretty large, right? I do 10 by 10 because they're easy to analyze, but easy and quick for it to solve. But it makes mazes like this. Now, you also notice that basically that you'll see a lot of recurring patterns in the maze, and that's because of the way I generate these mazes. I generate my mazes in a very specific way, in a very easy way, because I like them to be easy solved. And also, I needed something really easy to make my maze. Okay, so the maze itself is made up of cells, right? Each square. So let's go ahead and go back over here, right, to maybe a 15 by 15 maze, right? The maze is divided into squares, and each square is like, so here's a square, 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 here's a square. Each of these are cells. This is the layout of my maze. Each of these is a cell. Cells have walls, like plants, right? Okay, so they have a they can have a north, south, east, and west wall. So this guy has a west wall, an east wall, a south wall, but not a north wall. And the guy above him, of course, doesn't have a south wall, because if this guy doesn't have a north, he doesn't have a south. I just wanted to make that part fairly straightforward. All right, I didn't want you guys pulling your hairs out on figuring out how to basically figure out how to draw that. So each cell, it keeps track of whether or not it has these walls, and it also keeps track of what row and column it's in, right? Where in the maze is it located? Okay, and I haven't gone through this in like a year, so give me a second. All right, so it's got a paint component which basically says, hey, what color are we going to make it? And this just simply draws it takes the square, and what it does is that it draws the walls. So if it has a north wall, it will draw the appropriate walls for them. Okay, now the cell simply has a constructor which says simply the color of the wall is white, sets row and column equal to set its row and column equal to the row and column that it's at, and say, hey, we've got all these walls. And then so it doesn't decide by itself what walls it's going to have. So we get into the maze grid panel for that. All right, so here we've got our extra credit, which is to use the homework is to write an algorithm that will solve the maze for you, and I've got you started over here, and I'll go into what that does, but specifically I start you off with the stack, and then we'll go over how we use that to solve it. And I say, hey, here's your start, here's your finish, and I'm gonna make you and I'm showing you how to color things. You color the start of the maze green and the start of the end of the maze red. Okay. Okay. We also have this function called visited, right, which lets you know if we've seen them, if we've been to that square, which I'll get into a bit. So, how does this work? By the way, so first, before we go into like the theoretical, oh, how do you make a maze? How do I know what's where? Well, first thing we do is that when we get this maze grid panel, it takes in the amount of rows and columns, the amount of cells we have in here. We set that up, rows and columns, and then we create a rows by column array of cells, right? We take rows times columns cells and we make them, and then for each of them we give them the appropriate coordinate, add it to the maze, and then we run. Then I proceed to run two things: generate the maze and solve the maze, right? So this creates all the cells, it gives them the appropriate rows and columns, and then this runs the generate maze, and then this runs to solve the maze. Okay. So how do I generate the maze? Well, what I do is that I essentially go through everything that's not the top row. So if you're not the top row or the left, if you're not the top row or the leftmost column, what I do is I randomly choose. If row is equal to 0, then I choose one of these. Essentially, what I do is that I choose a random wall to remove. I either remove the north wall, or I remove your west wall. So for every square, every single square that I go through that's not a top column, a top row, or a column, what I do is I randomly choose the north square or your west square, and I remove a wall. And that makes it very easy to generate a maze. This is like one of the easiest ways to generate the maze, right? So if you're not this row or this column, I go to you and I go, okay, you're going to remove your north, you're going to remove your west, you're going to remove your west, you're going to remove your north, you're going to remove your west, you're going to remove your west, you're going to remove your west, and so on and so forth, right? And then every so often, and then here we removed our north, west, north, north. And then we go on to the next line, and so on and so forth. And that just simply creates a maze, and it kind of has this like windy diagonal passageway bias for generating it, but that's fine. It doesn't create the long winding corridors, it just creates these diagonal corridors. So we don't get a lot of things that wind back and forth here, just simply because of the way I generate the maze. But it was an easy way to generate the maze. That's why I call it NW maze for north and west, because I'm removing the northwest walls. And all I'm doing is I'm just simply going through and generating those walls. Okay. Now, how do you solve this maze? Well, I might as well show you my solution, but not the code. So what is your solution going to look like? Compile. A solution looks something like this, where basically I've got a green path that goes from here to here. Now you'll notice that I've got a dark gray corridor, that all these corridors are dark gray. And if you look very closely, let's see if we open up, right, you'll see that there's a black line going over here indicating a wall, but there's no such line here, meaning it went down this corridor. And this is because of the way this is designed. What my algorithm does for solving the maze, or the way you're going to solve the maze, is to use this kind of rope and chalk technique, right? Your stack is effectively your rope here. Every time you enter a cell, you enter it onto the stack. So whatever cell you enter, you push it onto the stack. You start here. That was automatically pushed onto the stack for you. Right? If we go over here, right, maze grid panel, we pushed our start location onto the stack, because that's the top of the stack is where you are. So now my algorithm, I basically say I start by trying to go south if I can first. I think my algorithm is south. Then, I think south, east, west. Sorry, south, west, north, and east as my order of directions. But you'll see. Basically, I chose to go south first, right? And I said, okay, so I get to this corridor. I can choose to go south, or I can choose to go east. And my if statement say I'm going to go down and check the south corridor. So pop this, push this onto the stack, 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 push, down to here. Okay, I can't go south, so so if I can't go south, I'm going to go east, and I can't go north because there's a wall there. I can't go to the east because there's a wall there. Can't go south, wall, and I can't go to the and if I go west, well, I've already been to that cell. Well, how do I know I've been to that cell? Because as I'm going along, I am coloring this thing green. I am changing the color. I am changing the color of my cell to green. How do I change the color of my cell? Right? This is me using the chalk function. I use the set background, and I just choose a color. And I use color green as my cell. Ooh, so I only have 22 minutes remaining. Wow, I went from 20% to 10%. Let's lower the brightness on. Alright. So next thing I want to do is... Oops, sorry, I think I lost my program. Alright. So I push all these onto the stack, and then when I get to a dead end, indicated by the fact that I've got walls and I can't go anywhere that I've already visited, I pop off this. I pop until I get to a location where I can visit. Right? It's the same loop. Basically, while I've got something to look at, right? The loop works something like this. While I still have something onto the top of my stack, I get my location by peeking at the top of my stack. I check, and I go in each of the cardinal directions around me, north, south, east, west, or whatever order you so choose. If I can go in that direction, great, I go in that direction. Otherwise, if I can't go in any of those directions, I pop off the location at the top of my stack. I can't go to that direction, and that effectively backtracks. And so I'm still in this while loop, so I get my new location by looking at the top of my stack. Right? Now, if I have to backtrack, I'm going to go ahead and paint that gray. So my loop looks something like this. Basically, if I can go in a direction, I'm going to push that location on top of my stack and paint it green. If I have to backtrack, I pop that location off the stack and paint that. Oh, sorry. I paint my current location gray, and then I pop it off the stack. So essentially, I just choose to go in this direction. So the way this algorithm worked, and let's go ahead and just run through this with a much smaller example, a 5x5. Okay, as I went down this corridor, I hit a dead end, so I pop. So then I push this location onto the stack and paint it green. Then I go down this corridor, because my algorithm at least is choosing to go south before it goes east. So I push this on, and I'm painting the galls green, push this on, paint it green. Oh, I can't go any further. I know this because of the walls and because this is green. I have this function in here you'll want to use called visited, right? I given a row and a column. If it's not white or it's not red, sorry, if it's white or red, then I haven't seen it before, right? White indicates I haven't been there. Whereas if it's green, I have been. Okay, so push those on, pop off, push all these on, pop off, push, pop off, and then I finally get to the end, right? And I'm painting these respectively as I go, and I get to the end, and that's it. And that's what I returned. So you'll be getting this and a write-up of this in your assignments for this week. The next videos will go over the cues, and I'll have those out tomorrow.